As I mentioned before, there's more than one way to define probability, and it's not. There's no one definition that's better than another. And so a simpler approach, a cleaner approach, is just to work in terms of axioms, and that's what we'll do now. But just to make things concrete, it takes a while to build up from the axioms to all the probability ideas. So just to make things concrete in your head, you won't be wrong. You'll be kept right if you think of probability this way. This is the frequentist interpretation of probability. So the idea is that if we have an experiment that we repeat n times, so we repeat it n times, and we're interested in an event E, so remember that's some subset of the possible outcomes, and suppose that occurs n times out of our trial, or n trials, then ne over n is the fraction of times the event happened in our n trials, and then what we do is we think about that fraction as the number of trials gets really big. Don't be thinking tens or hundreds or thousands, be thinking millions or billions, and then what that ratio becomes when you repeat the trial many times is probability. So it's the fraction of times. If you repeat the trial a huge number of times, the fraction of times the event happens is one way of thinking about probability. And so keeping that idea in mind, you won't go wrong, except in cases when you can't repeat the experiment an unlimited number of times, which of course is nearly always. It's very rare that you could repeat a trial so many times, and that's the problem with this definition of probability. Okay, so let's move on to the axioms. An axiom is supposed to be a self-evident truth. So when you see it, you think, yeah, that's reasonable. It shouldn't be something it should be very sort of atomic and simple. So here's the three axioms for probability, and it turns out that these are enough for us to build all of the theory of probability. We don't need any more. That this plus a couple of definitions will do the job. So the first axiom is if we have an event E, the probability of that event lies between 0 and 1. So what we're saying, that we can't have negative probabilities. The probability can't be bigger than 1. Okay? Remembering S is our sample space, so that's the set of all possible outcomes. The probability that something in that one of those outcomes occurs is 1. Now that's kind of a trivial thing, right? We're saying when we do the experiment, we see one of the possible outcomes, right? So these are very straightforward axioms. Axiom 3 is a little bit more complicated. It's about combining different events. Suppose we've got two events, E and F, and suppose they're mutually exclusive. What does that mean? That means they don't overlap. That means if I draw my sample space here, and this is E, and this is F, they don't overlap. They're two separate. There's no intersection. That would be a problem. So they're separate. And what we're going to say is the probability of an event which is a combination of, suppose this could be heads, for example, and this guy, could be tails over here, right? Drawing's pretty bad. So they're two disjoint events, and when we combine them, we're interested in a heads or a tails coming up. So that's the union of those. So probability of the combination is the sum of the probabilities of the individual events. So the probability of a head plus the probability of a tails is the probability of a head and a tail. And more generally, if we take the union of a series of events, of random events, it could be up to n of them. So that's the E1 intersection, E1 union E2 union E3. We just add things up. And they have to not be overlapping. We'll come back to overlapping sets shortly. It turns out, so this is the simplest sort of way of writing it. We can deal with overlapping sets just with these three axioms. So these are very straightforward, and incredibly, that's enough for us to create all of probability as we know it. And we'll be able to derive the proofs, and how you derive all different properties are very straightforward, and so we'll do it, right? You don't have to believe me that these probability ideas are true. It's not me as an expert propounding to you. Instead, you can convince yourself So as long as you accept the 3 axioms, then all the rest will follow from that. So let's start by looking at some easy implications of the axioms. So suppose we've got an event E. So remember, it's a set. Remember, that's why it's worth bearing in mind what we really mean by these events. E is a set, a subset of the sample space. Then its complement is not E, right? That means that all the things that are not in say E, is the probability of that is 1 minus the probability of E. And so that's a really basic thing. So here's how we get it from the axioms. So we know that the sample space is given by the event E plus the union with all the things not in E. So the things in E plus things not in E, that's everything, so that's our sample space. And we also know that E and its complement don't intersect, right? They're the empty set. We know that by our axiom, second axiom, probability of the sample space is 1. And by our third axiom, that's equal to the probability of E plus probability of E complement. And now we're done, because now if we rearrange this guy here, then we get, so we subtract probability of E from both sides, we get 1 minus PE is equal to probability of E complement, which is what we want. So this just follows from 2 of the axioms. And it's a really natural thing, right? So if we have, suppose our sample space was sunny, rainy, snowy, windy, so some weather, and suppose the event E was sunny, then E complement was rainy, snowy, and windy. Then what we're going to say is the probability that it's sunny is 1 minus the probability that it was rainy, snowy, windy, everything else, probability of everything else. It's already something that's going to be very useful. And here's another quite natural thing that follows from the axioms. Suppose I've got 2 events E and F, and suppose E is a subset of F. So this is the setup. This is our sample space. This is the set F here. Pesky to draw. And this is the set E, and it lies inside F, right? It's a subset of F. Then the probability of event E is going to be less than or equal to the probability of event F, right? So suppose the event F was the probability that a head or a tail came up when we tossed a coin, then the probability of E, suppose probability is the probability of a tail. Obviously the probability of a tail is going to be less than the probability of a head or a tail, right? And so this follows from our axioms using this argument. I'll let you follow it. So it's a slightly more complicated argument because you have to monkey around with sets here. And so I'll let you draw the pictures to let you understand that there. And then the rest follows. But do work through it because you can convince yourself it's true. It's nice. It's very straightforward. And here's the case when we've got 2 events, E and F, that might overlap. So now we've got something like this. This is our setup. This is our event E. This is our event F. And they're not just joined, right? There's this bit in the middle where they overlap, right? So, and we want to find the probability of E union F, so the probability of E or F happening. Now, if they were disjoint, the axioms tell us we just add the probabilities. But the problem with that is that if we add them and they overlap, then when we count the probability of event E, which is this bunch, we're counting the stuff in the intersection there. And then when we count the probability of the event F, we're going to count this stuff in the middle, the intersection again, so we're counting it twice. And so that's not right. So we have to subtract off 1 copy of that, so we just count it the once. So we calculate probability of E, probability of F, and then subtract off the probability, 1 copy of the probability of E intersection F, of that bit in the middle. So it's quite natural. And so again, I'll leave it to you to work through how that follows from the axioms in a really straightforward way. And here's another important outcome that just follows from the axioms pretty directly. So we make an assumption. So suppose all the outcomes of our experiment are equally likely. So when we roll a dice, we think all the numbers from 1 to 6 are equally likely. Or when we toss a fair coin, then head or tails are equally likely. Of course, if it's not fair, then they're not equally likely. But suppose they're all equally likely. Then we can start calculating probabilities. The axioms let us to actually put numbers on the probabilities, and we can start using our counting that we did earlier. So suppose we look at a coin, because it's nice and straightforward. Our sample space is heads or tails. The probability of, suppose, then this is an assumption, the probability of a heads is the probability of a tails, and we'll call that probability P. We don't know what that is yet, but we'll just call it P. So this is an assumption here then about our setup. But given that assumption, we can start to calculate what the probability P is, because we know that the probability of the sample space, which is the probability of heads or tails, is 1. That's our axiom. And we also know from one of our other axioms that the probability of a head plus probability of the tails is equal to the probability of heads or tails, right? That's the axiom 3. So the probability of heads is P, probability of tails is P, and we don't know what P is, but we're just going to solve the equation shortly. So that's equal to 2P. We know the probability of heads or tails is 1, so we know this is equal to 1. We're getting there slowly. Now divide both sides by 2, so this becomes P and this becomes a half. And so we get P equals a half. And more generally, if they're all equally likely, what we do is we count the number of outcomes we can get, and we take the probability of each one is 1 over the number of outcomes. And that's for the individual outcomes. And then when we have events which combine multiple outcomes, for example, if we roll a dice and it's whether we get a 3 or a 5, that's 2 outcomes, so we add it twice. So that's where using our counting lets us get probability, provided we make this assumption that things are fair. So here's another example. Suppose we've got a set of outcomes 1 to n. That's our sample space. And we suppose the probability of each of the individual outcomes is the same. Then we're going to get the probability of each of the outcomes is 1 over n by exactly the same argument. And if we've got an event E, so I'm just repeating myself now, if we've got an event E which contains multiple outcomes, suppose it's that we got a 1 or a 2 in this example, then the probability of E is going to be the number of outcomes in E over the number of outcomes in S, which the size of a set, when I write a set with 2 vertical bars, that's the number of elements in a set. So it's the number of elements in the event divided by the total number of elements in the sample space. So if E was 3 and 4, so a 3 or a 4 comes up, S is 1 to 6, then the probability of E is 2 over 6.